Okay, now that we are armed with all of these definitions about cryptography, what it is, and how you analyze schemes for their security, let's go through a brief history and see how cryptography has evolved over the years. And along the way, we'll get a chance to apply some of our definitions to schemes from many, many years ago. And we'll see how secure they are, how insecure they are. So that's our goal. So we're not going to test you on any of these really old cryptographic schemes, but it's a good chance for you to apply the definitions that you've seen so far and see if they make sense. So let's go all the way back to thousands and thousands of years ago before computers were a thing. We are talking prehistoric times now. One of the very first cryptographic schemes, according to legend, is the Caesar cipher. It's a very simple scheme. And remember, when you define a cryptographic scheme, you define it in terms of the encryption function, the decryption function, and the key generation algorithm. So even though I could tell this to you in English, I'm going to use our definitions so that we get a chance to practice with the definitions that we've seen. So the first thing I will do is define how Alice and Bob agree on a key. All they have to do is pick a number between 0 and 25. Those are your keys. So Alice might say, my key is 13, and Alice and Bob agree on 13. Or Alice and Bob might say, the key is 24, and they agree on 24 as the key. That's how you generate a key. Alice and Bob know the secret number. No one else does. That's the key. Now we'll define an encryption scheme. The encryption scheme takes in two arguments. One of them is the key. That's your number between 0 and 25. And the second thing is the message, which is, for now, we'll assume it's some English word. And the encryption scheme works like this. For every letter, you increment it k times. So for example, if you have the plaintext dog, there's a lot of dogs today, and the key is 3, you would just take D, and you would count 3 letters up, E, F, G. So D becomes G. O, you count 3 up, it becomes P, Q, R. And then G, you count 3 letters later, it becomes H, I, J. So encrypting dog becomes G, R, J. That's the scrambled ciphertext that you send across the channel. That is the encryption scheme. And we showed it to you in this very mathematical way. So what's the decryption scheme? You just do the thing in reverse. So you take the ciphertext and you count each letter 3 backwards in the alphabet. So for example, GRJ, well, I start with J, and I count 3 backwards. So you practice reciting your alphabet backwards. It goes J, I, H, G. So the J becomes a G, and likewise the R becomes an O, the G becomes a D. So Bob is able to recover the original ciphertext dog. So this is how you define a scheme using the functions that we've talked about. It's a very simple scheme, but more complicated ones will be coming later. So how do you break it? Well, let's say Eve is an attacker, and she sees this ciphertext. I don't know what that says. I don't know what the key is. Eve doesn't know if the key was 0 or 5 or 25. So when she sees this, she doesn't know how to decrypt it. That's the goal of cryptography. We don't want Eve to be able to read what this message says. So if you're Eve and you need to break this scheme, what would you do? One very simple thing you could do in this case is try all the different keys. So try decrypting this with key 1. And to decrypt it with key 1, you take all the letters and you count backwards by 1, and you get ibajimum divatibus. Okay, so maybe that's the message. Maybe they were using some old language, but I don't think that's it. And then you can try with key 2, count all the letters 2 letters back, and then try with key 3, key 4, key 5, key 6. And what you do is you just write out all the possible decryptions with every different possible key, and maybe that gives Eve a clue as to which is the correct plaintext. What do you think is the correct plaintext here? You think it's Vawazakwaskoff? I don't think so. What is it? I think it's Hail Caesar, because that's the only one that is intelligible English. So here's the case where Eve is using a little bit of existing knowledge and reasoning that that's probably what Alice and Bob meant to send. But what we're showing here is that one possible attack that people might try is a brute force attack, where they try every possible key and see what the possible plaintexts are. That's what was achieved here. So this scheme is not very secure. It is vulnerable to an Eve trying 26 different keys. And I think that's the original message, unless they were talking in some alien language. We can also try a different attack. So remember our chosen plaintext attack model? And remember, the chosen plaintext attack model says that Eve has an extra power. And the power is that she can trick Alice into encrypting any plaintext she wants. If she sends a message to Alice, Alice has to faithfully encrypt it with the key, and send it back to Eve. So what if Eve exercises this power and she says, Alice, I want you to encrypt AAA. And Alice has no choice but to take the message AAA, faithfully encrypt it with her secret key, a number between 1 and 25, and give the value back to Eve. So Eve says, please encrypt AAA, and she gets back the answer CCC. Doesn't this give Eve a clue as to what the key is? If Eve knows that AAA encrypts to CCC, well, she can reason that to start from A and go to C, you have to increment by 2. That must mean that the key is 2. And now she doesn't even have to brute force. She has the key. She can decrypt the ciphertext. So if you have the ability to attempt a chosen plaintext attack, we're giving Eve quite a bit of power. She can do things like this, and if your scheme is not very secure, you might end up leaking the key to Eve by giving her these plaintext ciphertext pairs. So this is why chosen plaintext attacks are dangerous and why we want to protect against them.